And thank you for turning up, which was a pleasure to see familiar faces and some new faces, I think, as well. The simple parish notices tonight, we have 2 speakers. And I just want to say that the Christmas lecture is on Friday, the 1st of December at 19:30 GMT, UTC, and it will be on active galactic nuclei by Professor Clive Tadhunter. So we can look forward to that one, and it puts the meeting back into its regular slot in the first Friday of the month. If anybody's been confused by the movements of this one to a later date, our apologies, but that's how it works out with the speaker. Tonight's speaker, this is one I've been looking forward to, I must confess. I've had some correspondence, and so had Paul, with some of the staff at Boulby Underground Laboratory, which is part of the UK's national science infrastructure. It's been there for some time, doing various experiments over the years. It's in a deep mine, which I'm sure we'll be told correctly what was mined out of it. I think it was gypsum rather than, it's not a coal mine. It's been there, and the director of Boulby, Professor Palling, is going to speak to us tonight around the search for dark matter. Now, I have one question which I would like to see answered. I was at an exhibition once and somebody was selling apparently empty boxes labeled, "This box probably contains 1 particle of dark matter." I'd like to know whether he was having me on or had a genuine claim that he could have a box with 1 particle of dark matter. So, Professor Palling, the floor is yours. Welcome.
Thank you. Thank you. Thanks for that introduction, and thanks for everyone joining and giving up some of your time. Andrew, I will be able to answer that question for you about the particles in a box, I hope. Right. So I'm gonna share my screen, if that's okay. Let's see if this works. Can you all see my screen? Can someone put a thumb up or something like that? You can see it, okay. Thank you very much.
Yes, we can.
Great. All right. Well, thank you. So I'm Sean Paling. I'm the director of Boulby Underground Laboratory, which is a deep underground science facility operating in the Northeast. And I'm going to talk to you all about that. So what you're looking at there in that picture, that is Boulby Mine. And it's a working mine, and it's Britain's deepest, biggest and busiest mine. It's 1.1 kilometers deep. It used to mine potash, which is potassium chloride, and it's a rock though, potassium chloride, and it's used in fertilizer in agriculture. And it's been mining that for something like 40 and a bit years. Recently, it started mining a different rock called polyhalite, which is also used in agriculture. So it's very much a working mine, deepest mine in Britain, deepest working mine in Europe. And if any of you know anything about mining, mines are amazing places, and particularly this one from an engineering point of view. What humans can do with some money and some machinery is incredible, never more so than in this place. So it's an amazing place for mining and industry. It's one of the big industries in the Northeast, about 12 miles north of Whitby. And if you know that area, a little similar distance south of Saltburn in the same area. But as well as it being amazing for industry, it's also amazing for science. And partly because we operate this underground lab, which is a picture on the bottom right, this amazing underground science facility in this working mine, 1.1 kilometers underground, and it allows us to do lots and lots of science. One of the areas of science it allows us to do is particle physics, strangely, and particle physics as it meets astronomy, strangely. And that is answering the question of what the universe is made of, because as you all no doubt know, there's an awful lot of evidence that suggests that when you look at the night sky, what you see is only a part of what's out there. There's a lot of evidence that suggests there's missing matter out there, some sort of gravity-giving stuff that is there, but we can't see it. It's matter, hence it's gravity-giving. There's more pull of gravity going on in space than we can explain by the laws of physics and by what we can see. We can't see it because it doesn't give off light, so it's become called dark matter. You'll know. As well as that, you may know there's lots of when you look at all the evidence out in the universe, it kind of guides you to what this dark matter might be. The best bet of what it is at the moment is some sort of subatomic particle that are everywhere in the universe, not just up there, but down here too, probably passing through you right now as well. And the idea is that each of these particles, each one weighs a small amount, but on the whole can make up something like 85% of the matter in the universe. And we even know what these particles must behave like. And there's a very prominent candidate range of particles called WIMPs you may have heard of. These stands for weakly interacting massive particles. They say what they are on the tin. They weakly interacting means they don't bang into matter very easily. They can pass straight through you and things very easily. And they're massive and they're particles. So this is 85% of the mass of the universe that seems to be missing. It's one of the big questions in physics to try and understand what's going on there. And the way we try and solve this mystery is by going deep underground in a mine like ours and operating very, very sensitive particle detectors away from interference from other particles on the surface of the Earth that you and I are being bathed in now, these things called cosmic rays. So going underground provides a quiet place to get away from that. And so one of the things that we do underground at Boulby Underground Lab is search for dark matter. But there's a lot of other stuff you can do as you go so deep into the bowels of the Earth. As you go into the Earth, you're going back in geological time. You can tell a lot about the Earth as it was then and how it's evolved and how it is now and what it might go to too. So there's a lot of Earth and environmental science. There's a lot of other particle physics and what we call low background radiation science you can do. And there's also biology underground at Boulby that is of kind of an extreme kind. It pushes the limits of understanding of how life can exist on Earth and exist on other planets. So we have teams who are interested in life and other planets and what that might look like come to Boulby to develop instrumentation and test their wares. So what I'm going to try and do is tell you all about that. Tell you exactly what I've just told you, but in a bit more detail. I've been told your talks are normally an hour. I will endeavor to speak less than that. I'm just going to check my timing. I will speak less than that, about 50 minutes maximum. What I'm going to do is tell you about a little bit about the search for dark matter, why we think it's there, what we think it is. Then I'm going to tell you about Boulby Mine and the underground lab that we've got there. And what I'm going to do is tell you the latest results in the search for dark matter around the world. It's a race to find this dark matter from the various different labs that are operating in the world. It's such a big thing to prove or disprove this. So a lot of people want to do it. So I'll tell you about the latest results. If I've got time, and I will keep an eye on the time, I will also quickly tell you about some of the other science of Boulby, in particular the astrobiology and planetary exploration work. I also want to quickly say what we're trying to do at Boulby in the future. We have an opportunity to build the world's great dark matter detector in Britain and up in the Northeast, and I want to tell you about that. So,
sorry there, can I just interrupt for just a second?
Yes.
Yes, so I'm the speaker after you. And just to say, I'm sure everybody listening in today is really keen to hear everything that you want to say. So I won't personally be offended if you go over time and I get less time, because I actually have some more time myself at the beginning of January. So it's not the end of the world. I
really, really appreciate that. Paul, you said to me an hour. I will be less than an hour. But thank you for saying that. I will say, so please, now, you all are experts in astronomy. I am not an astronomer. I'm a particle physicist. I mean, at a stretch, we're called astroparticle physicists because what we're looking at is particles in space and what we're interested in. But you are astronomers, but you no doubt know quite a bit about dark matter, and you may also know about particle physics. What I'm going to present to you here is at a very basic level. Please do not feel patronized. I'm not trying to patronize you. I'm just going to explain it at a basic level. Please ask me complicated questions, probably at the end. So be aware some of this is basic. Please don't feel patronized. That's not my intention. It's just, I'm also told that some of you may not know about dark matter. So I'm going to go that way. Okay, so that's my plan. Right. So first of all, everything there is to know about dark matter in 3 slides, if I may. So first of all, why do we think dark matter exists? Again, forgive the basic nature of this if you're experts already. Well, first of all, the problem is when you all sorts of evidence of looking up in space and also trying to understand how the universe works and trying to understand how it's got from the Big Bang to what we see now, many sorts of evidence suggests there's more out in space than we can see. And when you add it up, it's something like 85% of the matter in the universe seems to be missing. What you see, what we think you see, we see when we look in the night sky, something like 15% of the matter out there. Now, there's lots and lots of evidence, as I say, things from gravitational lensing, looking at how matter bends light, looking at large-scale structure formation, so how the various structures in the universe has formed since the Big Bang, analysis of the cosmic microwave background. All of those require there to be something more than we can see for it to make sense. But probably the most obvious bit of evidence for dark matter being out there, as you'll know, is how things move in space. There appears to be much more pulling of gravity going on than can be explained by what we can see. And that accounts for galaxies, galaxy clusters, and bigger structures as well. Galaxies are the most obvious, though, perhaps. If you look at the picture on the bottom right, you'll know that galaxies, big rotating masses of stars that they are, the laws of physics that work at those scales should be basically, relatively simply, the laws of gravity in terms of how fast things can move. And so a few decades ago, Vera Rubin in the States, was one of her many jobs was to go and look at some galaxies and just test out that the dynamics of the galaxy make sense. By Newton's laws, the heavier the galaxy, the faster it should be able to rotate without those stars flying apart from the pull of gravity of the center. What she found out, starting off with Andromeda, was the galaxy, similar to this one, not this one though, was rotating too fast. So if you look at this plot here, on the bottom is distance in light years from the center of the galaxy. At the top is the velocity of the stars that are being measured. Okay, and if you look at the dotted line, that should be the prediction of Newtonian or Einstein's gravity. But what she found was no, as you go out to larger radiuses, these galaxies, that galaxy is spinning much too fast, of the order of a factor 3 out in the outer reaches too fast. And it's not just this galaxy, it's many, most galaxies appear to show this behavior. And so the simplest interpretation of what's going on here is, could there be some missing matter in that picture that you're looking at that's having that extra pull of gravity, that's allowing the galaxy to rotate, but not the stars fly apart? So this is the most obvious evidence for dark matter, but there's lots of it. Next, though, the question has been, is what is this dark matter? And I'm going to cut a long story short here, but for a long time there was a question, is it big things or is it small things? If any of you knew about this at the time, these were categorized into machos, meaning massive astrophysical compact halo objects, and WIMPs, weakly interacting massive particles. The WIMPs are definitely winning out. It definitely appears to be small things, not big things. Searches for big things out there don't add up. And if you look at structure formation and how things form, it's very sensitive to the mass of the missing matter particles. And, you know, it does point to particles of a type. So we think it's particles. And we know a lot about particles, thanks to, you know, clever particle physicists and lots of money that goes into the CERN work in, you know, the LHC at CERN. We know a lot about particles in nature now. You'll know we have kind of a standard model of how all of the matter that we readily come across works. So we have atoms, of course, we have neutrons and protons, and in that we have quarks, gluons, etc. And we have electrons and muons and neutrinos and all these wonderful things. We know a lot about particles. We know how they behave. We also know about the 4 forces in nature that work. We know a lot. But could it be any of these normal particles that we know about, and really none of the particles that you look at there, including neutrinos, which are a candidate for dark matter, because neutrinos are passing through you and me all the time now, and each of them weighs a small amount. Could they make up the missing mass in the universe? And we really think no, none of them fit. And the evidence points to something heavier than neutrinos, which we know exist in nature. They're the most abundant, neutrinos are the most abundant particle in nature, apart from photon, so the most abundant massive particle. Billions are passing through us per day. But no, they don't fit. They're not heavy enough. The evidence points to there being some new, beyond the standard model, weakly interacting massive particles. The evidence tells us something about the behavior that would fit the evidence. These particles need to be heavy. They need to have no charge, no positive or negative charge. Otherwise, they would bang into matter easily. But they need to interact weakly, so they can. All the evidence suggests that they should be able to pass through matter relatively easily. Occasionally, one should be able to hit. The likely mass of these particles, which you can tell from various bits of evidence, or you can infer from various bits of evidence, is likely to be quite heavy, likely to be, not definitely, something like 10 to 1,000 times the mass of a hydrogen atom. That's a lot. So, and yet these particles could be passing through us and all around us as we speak. Okay, so particle physics, the LHC and all that, although they're very proud of their standard model, they do know that there's more out there than their standard model. There are things that don't fit, and they have suggested particles, and this is one called the neutralino, which would fit dark matter, but it hasn't been found yet. It would explain dark matter. But where we've got to is this. The model is this. The dark matter particle WIMP model that seems to be the most favored model there may well be particles passing through us as we speak. Something like, if you were to hold out your hand, something like 20 million going through your hand per second. These are relatively heavy particles beyond the standard model, but because they weakly interact, they don't bang into things easily, we expect less than 1 per month to hit your hand, less than that. Okay, so this is the experimental problem, to look for this and to prove and to prove if this is true or not. So a summary of all that, and again, I'm sorry if this is too basic for your knowledge. Feel free to dig deeper later. So dark matter in a nutshell, something like 85% of the matter in the universe is missing. Virtually every bit of evidence appears to show it, broadly speaking, of how we understand how the universe got to where it is now from the Big Bang, and many of the observations we make as well. And the best candidate of what it is weakly interacting massive particles. It's not the only one, but it's the best one. It's the favored candidate. Solving these problems is like solving a crime, as you'll know. You've got these various suspects, some of which are glaringly obvious suspects, some of which are a bit more out there. The glaringly obvious one is some sort of particle, but we'll see. Anyway, so what we're saying is that when you look at the night sky, what you're looking at, as well as the stars, there's more out there than you can see. And it's not just insignificant stuff. So obviously, when we look at a cityscape, you look at the lights, to the untrained eye, you'd think that's all that's there, but we know there's much more structure in there that we can't see. It's actually the stuff that's doing most of the, that's creating most of the structure. So does dark matter matter? Yes and no. I mean, no, in that, we've managed to get through our days so far without understanding dark matter, and, we're okay, aren't we? But does it matter astronomically and cosmologically and from a physics point of view? Absolutely, yes. Like that picture on the bottom left, the idea is that this is 85% of the mass of the universe. It holds the universe together. Wherever gravity is a significant player in astronomical objects on a large scale, it's the dark matter that is the dominant stuff, not the light matter. So the evolution of the evolution of the universe from Big Bang to now, if the dark matter theory is correct, has been dominated by the dark matter, and the light matter has followed. So yes, it is important. And lastly, is this all true, what I've just said? And the answer is, we don't know. We follow the evidence, and it points us in this direction. And I'm an experimental particle physicist, or experimental astroparticle physicist. So the job of me and my team, is to find out if it's true. And it's, as I say, it's very much a race. So that's the theory. What I'm going to do now is go on to tell you about how we prove if it's true or not. And the way we do it, forgive me if this is all very familiar to you, the way we do it is with not simple, quite the opposite, but with sensitive particle detectors. So what we're looking for is, the idea is these dark matter particles all around us, passing through us as we speak. If we can build a detector that can go ping, which is what a particle detector is, detector that goes ping when a particle hits it, and we take it somewhere quiet and look for these particles. This is the way you look for dark matter. So how you build a dark matter detector is simply you build a particle detector. And particle detectors look like this on the left-hand side. There's two important parts, really. You have a target material of some kind, and then you have a data acquisition system. What I mean by a target material is a material that gives off some kind of signal when a particle hits it. So you'll know Geiger counters, which they're gas-filled things that give off charge when they're hit, and it causes a click. You've got your particle detector. These things on the right-hand side are scintillators. That's another type of particle detector. They're often plastic or different liquids or other crystals or things like that. And what they are is they're called scintillators. And when a particle hits them, they give off a little flash of light. That's an example of a scintillator, and that's an example of a target. Now, as well as a target, you need a data acquisition system. And what that does, that's a system that turns that signal that's been given off and allows you to record it by a computer in some way. So in the case of a scintillator, what we use is these photomultiplier tubes that you can see in the middle picture there. These are very, very sensitive electronic eyes. All they are is almost the reverse of a television screen, the old cathode ray television screen. Photons come in from the front. They kick off an electron from the front window. That electron is accelerated leftwards in the picture, and out you get is a big blip at the back. You got an electronic pulse, you can record it on your computer. So that's how you make a particle detector. And in case of a scintillator, you get that bit of plastic, you stick it against that light detector. Your code comes in with a particle detector, and that's broadly how you build a dark matter detector. In practice, our dark matter detectors are a lot more fancy than that, and I'm going to come back to this, but this is what they look like. There's two detectors I'm showing you here that were both developed at Boulby in the UK. The UK has been brilliant. UK has got some wonderful things, hasn't it? It's got wonderful musicians, but it's also got wonderful scientists. And the UK has been really influential in how to find dark matter and developing these techniques. And these are two of the detectors that have been developed at Boulby. One is called Zeppelin, this stuff on the left-hand side. This is a scintillator. And this one on the right-hand side is more a gas-filled thing. This is called Drift Cygnus. This is more like a Geiger counter, very fancy Geiger counter. This is what they look like, fancy particle detectors. Now, wouldn't it be good? I mean, this is particle physics, but it meets astronomy, so it's astroparticle physics. You might know that particle physicists, they do their work at CERN. CERN is on the sort of Swiss-French border in the Alps. It's beautiful. The Alps are a lovely place to go, and that's where they go to do their work. A lot of astronomers, as you know, get to go to La Palma and to Hawaii and lovely places like that. This is a picture of Hawaii. Wouldn't it be good if we can take our particle detector, dark matter particle detector, and take it to Hawaii? Unfortunately, the answer is no. And the reason for no, I can't take it to Hawaii. I can't take it to the Alps. The problem is anywhere on the surface of the Earth is bathed in natural radiation. You've got some coming from the materials all around us, from the rocks and in the air. Even you and I, we're all slightly radioactive. But the really difficult stuff to shield against is cosmic rays coming from space. So high energy, charged and non-charged particles bombarding us. And to get away from that, you can't shield with lead. It's just not enough. You need to go somewhere with a really big roof above your head, which is why we're at Boulby Mine in the northeast. So now I'm going to tell you about the Boulby Mine and the lab there. So this is Boulby Mine. As I say, it's Britain's deepest and biggest and busiest mine. So it's owned by and run by a company called ICL. It's changed its who owned it over a number of times in the last 50 years. So ICL is an Israeli company, actually, Israeli Chemicals Limited. It's a big industry in the region, employs 500 people directly, something like 2,000 indirectly. They mine this stuff called polyhalite now. They did mine potash. But now they mine polyhalite, and it's used as a fertilizer in agriculture. It's never been more profitable than now, with all the things that are going on with commodities, with the various troubles around the world. And here we are up in the northeast, just north of Whitby, beautiful town of Whitby, if any of you know that area. A bit more about the mining there and what they mine. What's mined at Boulby used to be a sea 250 million years ago in this picture on the top right. This is called the Zechstein Sea. It used to exist in that region. You can see where it cuts across Britain 250 million years ago. When that sea evaporated, it left a layer of salt, sodium chloride, down here on the bottom left in the green stripe. And above it, if you evaporate a sea, if there's enough potassium chloride in it, you get potassium chloride, a layer of potassium chloride. That's potash, this stuff here. And if you look at our map, this is a local area of the map underground. The red roadways are mined into the salt at Boulby because salt is relatively structurally sound. That's this picture here. This is what a salt roadway looks like. When they want the potash, they dig upwards to get the potash, and these are the grey roadways here. And then they convey about the potash all the way out. So they've mined 1,000 kilometers of tunnel looking for potash out under the sea and under the land in 50 years. That's more than the Channel Tunnel worth per year. But they found that they were mining so far away from the shaft, they needed to mine something else. So it was getting too expensive for the 45-minute drive underground in the morning they have to drive to go and do the mining out there. But anyway, they found 200 meters below is this other stuff called polyhalite, which is an even better fertilizer. So they're now mining that. That's what they mine there. Anyway, there were two shafts at Boulby here, the two red dots, one for people going in and out and one for rock coming out. And about 800 meters from that shaft is our laboratory. We've had various laboratories over the years, actually. We started, the first laboratory at Boulby was put down there. Well, it wasn't even a laboratory, it was literally a garden shed. You're looking at it there. That was in it's actually late 1980s, early 1990s, when scientists first realized they could build dark matter detectors, particle to take them underground, and you can actually find this dark matter. So it was realized about a bit over 30 years ago, a bit more than that. And this is what our labs look like, and they evolved slowly. Quite recently, about this one called the GIF area of 2003 to 2015. And most recently, we have this wonderful laboratory that you see a schematic of on the right-hand side. This is the laboratory we're in now, 1.1 kilometers deep. The cosmic ray rate is reduced by a factor million. So it's 1 million times quieter there in terms of particle interference than where you're sitting now. This laboratory is operated by one of the research councils called STFC, Science and Technology Facilities Council. It's the funding council that funds astronomy and particle physics in the UK, but it also funds facilities. The facility, when you're inside of it, looks like this on the left-hand side. This picture is a very early picture. I know that because we now operate as a clean room, and we wouldn't allow, we go underground wearing mining gear. This is what you look like when you're in the mine. We don't allow that in the lab now. This is what it looks like in the lab now. And this is some of the team that work down there. We operate it as a full clean room. So we have this wonderful underground science facility for running all sorts of science. We have this surface building on the top left-hand side for admin and getting changed and sending things underground. We also have this on the top right-hand side, we have this kind of outside play area. Because remember I said there's a lot of other science that can go on in a deep underground lab. And we host biologists and geologists who actually, and some of them don't want a lab, they want access to the geology. So we've created a play area for them, and it looks like this. Here is a map of our current laboratory here, and just outside of it, we have this kind of outside play area to allow different scientists to run different projects in 1.1 kilometer underground, 250 million year old salt, which has got biology in it that looks similar to how biology might look on other planets. So that's what we've got at Boulby. And just quickly, this is a very busy slide, and I won't go on, but this is just the facts and figures of Boulby. First of all, I will say, if you look at the map here, I know you can't see it very well, but there are only a few countries in the world that have underground labs. There aren't many places in the world you can get access to deep underground like this, safely, reliably, and with space underground to build experiments and have ability to transport equipment underground. So we have this working mine that allows us to use that space. It's a wonderful thing. But there are 12 underground labs around the world. There's some big ones. There's a big one in Japan, big one in Canada, big one in, well, not big, but important one in America, and a really big one in Italy. And Boulby is not the biggest, it's not the smallest, it's not the deepest, it's not the shallowest. What I would say is it's, first of all, one, we have the lowest radon levels. Anyone of you know about radon in the world? We have the lowest radon levels of all the labs. We have the most diverse science program of all the labs. All the labs, if they're deep underground, can do dark matter research, but our geology is so interesting to geologists and earth scientists. Our science program is really broad. But the other thing that's interesting about Boulby Lab is a science and industry partnership. Some of these other labs around the world are either under mountains, like if you dig a road tunnel under a mountain, you've got all that rock above your head, and you can create a cavern there, and you've got an underground lab essentially. But some of the others are in deep mines, but disused mines. We're in a working mine. And the good thing about that is that we get this in this country for something like a 20th of the cost that it would be if we had to keep the mine open ourselves. So it's a wonderful thing. And just to say, this is what our life is like working underground. We do work very much with the mine. We're, every day is working alongside miners. Our responsibility as a laboratory is to run the lab and support the science. We also do lots of health and safety, and to keep this miner generous in allowing us to be there. So we have a responsibility to make sure health and safety is as good as they need it and better. And the impact, our operations impact on their mining is minimal, and we do outreach and media in a way that is okay for them. What they do for us is keep the mine open. They keep us safe, and they deliver materials down and help us with, they give us high-level political support and things like that. So if I can, I'm quickly, if in the ideal world, I'd invite you all to Boulby up in the northeast and send you and take you underground. I can't do that. So instead, what I'm going to do is I'm going to show you a quick video of what it's like to go underground. This picture at the bottom middle is one of my team members showing you what you need to wear to go underground. We do go dressed as miners to go underground. And I'm going to show you the video of going underground and getting to the lab. This video is about 20 minutes shortened to about 2. So it's quick. So I'm going to show this quickly. Okay. You can see 2 shafts there. One was for people going in and out, one was for rock coming out. And we're going into the mine, what they call the lamp room here. This is where people pick up their lamps and their batteries to go, for their lamps and various other things. Now we're going into an airlock now, just at the top of the shaft. So this is going down into the cage now. This is the cage to go underground. Takes about 7 minutes. And that noise you were hearing was the air being pushed down. The way they ventilate the mine is pushing down the shaft that we're going in. It goes around the mine and comes up the other shaft. So this is arriving 7 minutes later at the pit bottom. So you're now in 250 million year old salt, 1.1 kilometers down. And it's about a 15-minute walk, one of Yorkshire's great walks to get to the laboratory. You're in 250 million year old salt, as I say. It's warm down there. The rock temperature is nearly 40 degrees C. You're closer to the center of the earth, closer to hell. So yeah, the rock temperature is what it is. So that's us arriving at the entrance to the lab. So the beep you heard was a tannoy system used by the mine. And what we'd done, if you look at the left-hand side, we'd gone down that shaft. We'd done about an 800-meter walk to get to the beginning of the laboratory, and that's where the blip was. And from then on in, we walk in, and the laboratory looks like that. So that's what it's like going underground. What I want to do now is talk more about the search for dark matter. So underground, it isn't as simple as that, as many of you will know. It's a real problem. And the main problem is, even though we go deep underground, there's still a lot of background radiation around, and searching for pings from dark matter particles or WIMPs is very much a needle in the haystack. The needle being the dark matter particle pings that you want to get versus the pings you're going to get from remaining background radiation. Even though you go deep underground, there's still radiation coming from the walls. There's radiation coming from the materials that you build your detector out of. So the way you actually build a dark matter detector, the principle is the same as I explained. But first of all, you need your detector to be as big as possible. The reason being, the bigger they are, the more pings you're going to get from dark matter, the more needles you'll get. You also need your detector to be low background. So you need to build it out of the lowest background material. So any steel you use, any glass you use, any material you use, you want to make sure it's not giving off, or you want it to give off the smallest amount of background radiation possible. So you have to select really low background radiation materials. That is an attempt to reduce your haystack. And finally, and the harder to understand one, is you need to make it discriminating. So you need to make it produce a different kind of ping to dark matter-like particles to background radiation particles. Background radiation tends to be charged, or at least work by the electromagnetic force. So things will hit the electrons of atoms, okay? Dark matter particles would not hit the electrons of atoms, it would hit the nuclei of atoms. So you can, there's something you can work with there to make a machine produce a different ping for background radiation than dark matter particles. So that's how you build a dark matter detector. And again, I'm going to show you pictures of different detectors. There's different ways to skin a cat from building a dark matter detector. So in the center is the basic model of a dark matter detector. You can make scintillator detectors, like I told you before, a piece of material that gives off a flash of light. You can make ionization detectors, like I told you before, like Geiger counters. One example is our wonderful Cygnus detector underground, which I'll explain in a bit. Or you can look for phonons. So when a particle hits your target, it can emit a small bit of heat. That's called a phonon. And there's various detectors that use that. And these are pictures of different detectors that use the different models. Some use a combination of two, like scintillation and ionization, for instance. And I'll point you at one of these called Zeppelin here, which was developed in the UK at Boulby. This is liquid xenon it uses as a scintillator, but it also gives off charge, ionization, and it uses the combination of the two to be a very, very effective dark matter detector. All of these are dark matter detectors that have been or are running in the world. The most sensitive at the moment are the technique using the system that was developed in the UK, this technique, the Zeppelin detector. Right. So what I'm going to do now is jump ahead and tell you the results we found so far, if I may. So the results so far are, have we found dark matter yet? So I will say that we're asked on a daily basis by the miners, have we found dark matter yet? We've been there for 30 years. They ask us on a daily basis. It's a difficult conversation. The answer is no. I think they think we're coming out with a bucket of it. It's not as simple as that. But I'm going to tell you that this is the most complex thing. I'll tell you where we are on the search for dark matter around the world. And there's a short answer and a long answer. The short answer is this: no, we nor our competitors stroke, what do you call them, community, have not found dark matter yet. But we are systematically narrowing the search, and that's the way it goes. And it is exciting times in the search for dark matter. It's very much still on. That's the short answer. The long answer is this. First of all, I want to show you this picture on the left-hand side. This thing I'm showing you here is the most sensitive dark matter detector running in the world at the moment. It's called LZ, and it stands for Lux Zeppelin. It uses a technique from the Zeppelin detector that we developed in the UK. And we're now still involved in this project, but we're running it in a mine in America, in South Dakota, in America. The lab is called the Surf Lab. It's running there. That's the most sensitive detector in the world at the moment. I'll come back to that. What I really want to explain to you is this graph here. And this graph here is the graph, or the playing field, if you like, on which the search for dark matter is fought, okay? And I'm going to explain it. So on the x-axis is the mass of the dark matter particle. Now, do you remember I said the evidence points us to what the mass of these particles is likely to be? It's likely to be over 10 times the mass of a hydrogen atom, over 10 GeV, over 10 times that. And it's likely to be less than 10,000 GeV, or maybe a bit more than that, somewhere between there and there. We don't know, but that's what the evidence suggests. The other thing the evidence tells us something about, a little bit, but not exactly, is how readily these particles will bang into matter. And if you look at the y-axis, but specifically look on the right-hand side, the evidence suggests that for every kilogram of matter, that could be kilogram of you, or it could be kilogram of our particle detector, you expect less than 1 hit per kilogram per day, even though there are billions passing through it per day, but more than something like 10 per 10 tons per year. Okay, and if you look at this blue splodge on this graph, This is the parameter space that describes. We know the mass is somewhere above 10, but actually less than 10 to the 5 mass. And we know it'll bang into matter less than 1 per kilogram per day, but more than 10 ton per year. That's what the blue splodge shows. And the way that the search for dark matter is fought is this. If we run a 1 kilogram detector and we don't find it, what we get to do, we don't find dark. If we find it, we find dark matter and we get a Nobel Prize, great. If not, we get to draw one of these lines on the plot that you see. For instance, there was an experiment called the Picasso experiment. It looked for dark matter. It did not find it. It got to rule out, oh, if I can do this, it got to rule out all of that above, okay? Then another experiment came along. For instance, the Coop experiment. That looked for dark matter. No, it didn't find it, but it ruled out more of that plot. And you see the Coop experiment overlapped into our blue region, so it stood a chance of finding it. And this is the way the search for dark matter works. We're gradually narrowing the search, if you like. We're ruling out different categories of particles bit by bit by bit. Now, on this plot, if you look, this line here, these are called limits. And when you set a line like that, it means you're removing everything above it. You've eliminated everything above it. This limit, the green line here, where it says Zeppelin 3, 2012, this is a line that the UK set in 2012. We were very, very, very excited by this line. We had not found dark matter, but we'd basically looked harder than anyone had. If you like, we were the best in the world at not finding dark matter, if you like. We had the most sensitive dark matter detector in the world. We'd ruled out more than anyone else. So with that wonderful technique, what's happened since is these other experiments have come along, Panda X, Xenon 1 ton, etc., and have set lower limits. And the best limit in the world at the moment is this LZ experiment on the left-hand side, Lux Zeppelin, in South Dakota. And the first results, they haven't found it. But can you see there's a long way to go? And the way this works, again, it's a systematic search. So we carry on searching until either we find dark matter, great, or we have to rule out that whole splodge. It's like looking for the keys in the house. If you lost your keys and you know they're in the house somewhere, you look in the kitchen, you look in the lounge, and you can't say the keys aren't in the house until you've looked upstairs and in the loft and all that. And so we're about halfway through, if you like, of the most likely set of candidates for dark matter. So that's where we are. Just a broader view of this. This is a broader view of what we're doing. This is the same plot, dark matter particle mass on the bottom, how readily it bangs into matter at the other. These are the most recent results. What's going to happen is the next LZ is going to carry on running and they will give us their results. But beyond that, there's going to be other detectors. Sooner or later, though, we're going to hit a new type of background from neutrinos in the universe, which is going to be hard for us to separate out. You can't shield against neutrinos, and we'll have to develop a different technique. But this summarizes where we are. We're sort of halfway through this orange splodge of the likely candidate for dark matter. That's where we are at the moment. So we might find it soon, or we might start to hit what's called the neutrino fog, but we will keep going. That's where we are at the moment. Right, I'm just going to check my watch. Right. If it's all right for you, I'm going to talk quickly. So first of all, what are we doing at Boulby at the moment? What do our detectors look like? This is what our current detectors at Boulby look like at the moment. We've really got two R&D systems at the moment. First of all, we've got this detector called Cygnus that I mentioned before. This is not the most sensitive dark matter detector in the world. That's running in America, partly because the Americans had more money to fund it than we did. But this is one of the cleverest dark matter detectors in the world. This is like a Geiger counter. It's gas filled. And the good thing about it is, as well as going ping when a particle hits it, and you get a different ping for dark matter than other things, it can tell you the direction of the particle that hits it, which makes it a dark matter telescope. And it is the most sensitive dark matter telescope in the world. And the reason this is a good thing is, as you know, we are in a galaxy and our galaxy is rotating. The theory of dark matter is that dark matter is everywhere, not just in our galaxy. And yes, we might have a cloud of dark matter around our galaxy, but our galaxy is thought to be rotating within it. Okay, so because it's rotating, there should be a preferential direction that dark matter particles are hitting us, or more to the point, we're hitting them. So if you start to get pings with a machine like this, and you plot them in galactic coordinates and you get a hotspot, you prove that what you're detecting is beyond the galaxy, is, you know, it's not some stationary point in our galaxy or in our lab that's causing it. We're moving within it. So this detector is running underground in the UK at the moment. When it's working, it's shielded and it looks like this. It looks very boring, but it, you know, it's there and it ticks away. Really, though, this is nowhere near as sensitive yet. The technology needs to improve to make it as sensitive as the one running in the USA. And so what we're doing is making this more and more simple to run, more cheap, and eventually we'd like to produce about 1,000 of these, and then it would be as sensitive as one in America. This will be the sort of thing people go to when dark matter first gets found. They'll want to say, how do we analyze it better? It'll be with something like this. Just quickly, another picture. I won't go on about this, but there's another R&D detector we have running underground at Boulby. There's no good picture of this, I'm afraid. It's sort of a picture on the bottom left. It's called Muse G. It's a little sphere. At the moment, it's only 30 centimeters in diameter. And again, it's like a Geiger counter, but it's spherical, and it's got a very clever anode sensor at the center that looks like this weird thing. And this allows you to detect very low mass and low energy signals. And it's only been realized in the last few years that this technique, if you scaled it up to 3 meters, would be the most sensitive dark matter detector in the world for lower mass dark matter particles. So we are running this in the UK at the moment at Boulby. The team that are running it want to build a 3-meter one out of pure copper that we grow underground to make it really, really pure, called Dark Sphere, and it would be the most sensitive in the world for low mass particles. That's the other thing that we're doing. And just lastly, we have this wonderful facility underground called BUGS, which stands for Boulby Underground Material Screening. And it allows us to run these very sensitive small particle detectors here. And they are not for looking for dark matter particles themselves. These are essential items used for selecting materials to build new dark matter detectors out of. Do you remember I said they need to be built out of really pure materials? The way you find that out is you get your material and you get a lot of it, and you put it into one of these detectors, and you get a spectrum of radiation out of it, and it tells you how good your material is. It allows you to build really sensitive particle detectors. So this facility, we don't just build our own detectors, we help the other teams in the world to build theirs too. It's a great facility. Okay, so summary so far is evidence, lots of evidence suggests that dark matter is out there. It's hard to find evidence that doesn't suggest that. We haven't found it yet. The race is very much still on, and the way it works is we're narrowing the search. This is not a random search. We're narrowing a search, attacking a certain parameter space. And in the UK, what we're doing is we've got these 2 R&D systems, we've got this germanium facility, but there's more to come, as I'll explain right at the end. I will say, if any of you get the chance to go to Whitby, obviously get in touch, but also please go to Whitby Museum. It has a wonderful old school museum in Whitby. And to that museum, we've given one of our most accomplished dark matter detectors in the museum. It's here. This is the Zeppelin detector. And if and when dark matter gets found, it's likely to be by this technique. And this thing will then be very, very famous. But it's sitting in Whitby Museum, which is a wonderful place by itself. So please go and have a look. Okay. If it's all right with you, I've got 10 more minutes, I think. If Andrew, will you nod if you're happy with me going on?
Please carry on.
Okay, so I'm going to come back to dark matter, but I'm going to take a complete sidetrack now and go to other science, and we'll come back to dark matter, but I will be 10 more minutes. Other science studies at Boulby, and what next? First of all, other science studies. I know this is a very busy slide. All I'll say is there's lots of other science you can do, from other types of low background radiation science, pure and applied, but there's also earth and environmental science, astrobiology, and planetary exploration. This picture here is using our BUGS detectors for gamma spectroscopy and environmental applications. This picture on the right-hand side is British Geological Survey exploring whether the salt can be used to store compressed air for energy storage purposes as humans go to sustainable energy. But the bottom pictures here, I'll move on to those. These are about astrobiology and life on other planets. So as I said, as I said, the salt that we're in underground at Boulby is 250 million year old salt. used to be a sea. It turns out, though, that wherever there's water running through that salt, there's microbial life in it of a kind of an extreme kind. Extreme, first, because salt is really known as to not support life. That's why it's a good preservative, because bacteria struggle to grow in it. But it turns out there is life that can exist in salt, and not only can it needs salt to live. They're called halophiles. So we have all sorts of biologists come underground to understand the limits of life on Earth. But as well as that, the life in the salt at Boulby was seeded there 250 million years ago and evolved relatively slowly and independently for 250 million years. And so teams who are now looking for life on other planets realize that life may not be on the surface. It may be safer and locked in underground. So we have a team of people, one wanting to understand the biology at Boulby, understand what biology might exist like on other planets, but also develop instrumentation to look for it. So I'm going to quickly show you some pictures of this. We have teams of people come underground to do just that. And I'm going to show you a quick video. Hopefully you'll be able to hear this. This just takes a couple of minutes.
Now, with the Mars rover continuing to make new discoveries and space tourism now a possibility, our fascination with the universe appears to have been rekindled.
One of the biggest questions, of course, for scientists has always been whether extraterrestrial life exists. Now it seems the answer might actually lie right here on Earth, deep in a mine in the northeast of England, as our science reporter Rebecca Morell reports.
On a journey beneath the Earth, a descent into one of Europe's deepest mines. We're more than half a mile underground. Here, miners have been extracting salt and potash since the 1970s, but these underground rocks hold something more.
Down here, it's dark, it's hot, it's dusty. You can even taste the salt in the air, but this kind of extreme environment is just like those found on other planets. And scientists say that studying the tiny organisms that live here could help them to find out whether life could thrive up there in space.
What we've got here is salt in contact with water. It's essentially table salt, sodium chloride. And the water here is a saturated salt solution.
It might look barren, but this place is teeming with life. Microbes invisible to the naked eye are everywhere.
So you look on Mars, you find table salt on the surface of that planet. If you look at Europa, one of the moons of Jupiter, you find a salty ocean beneath an icy crust. So there are salts everywhere in the universe. If you want to understand whether life might be able to originate and grow in some of these extraterrestrial environments and assess them as abodes for life, you need to come to a dark, salty environment.
The samples are taken to the subterranean laboratory. It's early days, but genetic tests are revealing unusual species in the mine. The hope is if life can cope with the tough conditions here, perhaps it could be found in the harsh environments beyond the Earth. Scientists say that the best way to understand extraterrestrial life is to start in places like this. Because while there might be intelligent, advanced beings out there, the chances are any aliens would be simple bugs like the ones found here. Rebecca Morell, BBC News, Boulby Mine.
So yes, so we have these teams of people come to Boulby and test, both to analyze the life, but also test equipment to go on the Mars rovers and the like. And these people actually come, our particle physicists and other types of scientists tend to come all throughout the year. These guys all tend to come at once, and they treat it like a mission to Boulby, like they would a mission to Mars. They come for 2 weeks, and we have this event called MINAR, which stands for Mine Analog, and it means the mine is an analog for Mars or wherever. And so, and they come and they test their equipment and just there for 2 weeks. We've just had the last MINAR we've just had. Literally last week it just finished, and so this was a big group we had. I think when was this, 2017? We had 35 people all at once. That's a lot of people for us to look after, testing various bits of equipment. We also had an astronaut down. This is Matthias Maurer, who's just come back from the space station. He was there to look at these bits of technologies and understand how they are developed. These are pictures, more recent ones, 2018 to 2022. Teams starting to bring mini Mars rovers to test the engineering, but it's mostly about the payloads that they bring. So imagers, scanners, 3D scanners, things that can sample rock and drill into rock. So far, we've had about 20 instruments tested at Boulby, 3 of which are going to go on the next European Mars rover when it finally gets sent. We also have a bit of this picture on the far left here. This is a bit of a Martian. You've seen the film The Martian. This is a team that are developing medical techniques that will need to be done independently from Earth when we go to Mars and populate Mars for so long. This is a team from Birmingham University developing those techniques in there. Anyway, so that's that. Just lastly then, I quickly want to say what next for dark matter at Boulby. So forget life on other planets, back to dark matter. And just a couple of slides. So do you remember I said the most sensitive dark matter detector in the world is this, and it's running in South Dakota. It's this thing called Lux Zeppelin. They haven't found dark matter yet. They are running in their most sensitive mode now, and this year, or at the end of this, sorry, a year from now, they will have published their data, and they will either have found dark matter or hints of dark matter, great, or they will have ruled out a bigger explosion than anyone has done before. Either outcome, they are going to want to build another one, either to find more out about it or to search the rest of the parameter space. And this team have already started collaborating with their competitors in Italy mainly, called the Xenon experiment, to plan the next experiment, which is going to be called XLZD, terrible acronym, but buried in there is the Z, that stands for Zeppelin. That's how the whole thing works, which was developed in the UK. Now, that experiment does not know where it's going to go yet, and we would very much like this to come to the UK, to come to Boulby. There are 5 labs in the world that are vying for this, and Boulby is one of them, and we have a very good chance. So could the next great dark matter detector come to the UK? We think so. And there's a lot of other science projects that would like a bigger lab than we've got now, and this is what we're looking at. So what we're doing right now, as well as running the current lab and doing all the stuff that we're doing, we've gone to the UK academic community and said, you're the experts on dark matter. What would the lab like? What would a new lab need to look like at Boulby to host a dark matter detector? And they say your current lab is nowhere near big enough. You need a bigger lab. The main cavern needs to be about 25 meters by 25 by 25. Quite a big lab. We've been to the mine. We talked to the mine a lot. They've designed us the type of lab that it needs. We've done costings. We've done timescales. The outcome of this is we know it is feasible. It's definitely well motivated and it's timely. So that was a feasibility study. And this is really my last slide, and I'm not going to go through it, but we are pushing now to try and get this next great dark matter detector to come to the UK. We're pushing for a major new lab to be built beside our current one up in the northeast, down in that mine. It could host the world's great dark matter detector that could be the one that finds dark matter finally. All rules it out. That's the job of science, but it will do all the science that we already do and more. And it would be a wonderful thing for the northeast. Great, cultural impact and economic impact and all those things. So that's what we're trying to do. So we will see. So that's it. So thank you very much for listening. What I will say is, if you're interested in this, any of this sort of stuff, please get in touch. Please, if you're social media fanatics, please look for us on social media, like us on Facebook and all those things, and just get in touch. Thank you. And I think I'm a little bit lower than an hour, so I went on longer.
Sure, that is fantastic. Thank you very much.
Very well.
Questions? Are there any questions, Sean? Either unmute yourself and shout them out, or pop them into the chat.
Hello. I have one question. It's probably a silly question.
No. Yeah.
We know that dark matter is gravitational active.
Yeah.
Are there any gravitational detectors? I'm thinking in terms of maybe a cloud of dark matter swinging through the Earth and changing the gravity slightly.
Well, we have a wonderful gravitational detector in the form of gravitational lensing, of course. So we've got that, but nothing. Yes, no. I've never. That's an interesting question, and a good one. I'm just trying to. My first answer is, that's not the way we look. We're trying to find it more directly than that. Is my first answer, but. Using gravitational lensing, we can already see that light seems to be getting bent by stuff that we can't see, and light is getting bent more by a galaxy than it should do by what we can see in it. So we already detect that. We're not really particularly thinking of there being fast-moving turbulence in the dark matter distribution. So we don't expect to see sort of gravitational waves or changes like that. But it's an interesting question, and I need to think more about that. But my first answer is yes, we have it in the form of gravitational lensing, but it's an interesting question. Let me think more about that. It's a good one. Thank you. And please, by the way, no question is too stupid. So do ask basic questions about the. We get asked some really strange questions, not strange, lovely questions, all the way from very deep particle physics all the way to how do we go to toilet underground. Anything in between is acceptable, and any of those are fine too.
Can I fire a quick question?
Anyone?
Martin's got his hand up. Can I just let Martin?
Yes, probably best if you put your hand up if you can, or something, and let Andrew pick the question is probably best.
Martin, you're muted at the moment. Martin, you're
Sorry.
muted. That's better.
Yeah, apologies for that. Sorry, man. You know how my hearing is absolutely dreadful. But just first of all, Sean, can I say thank you for an absolutely wonderfully informative and entertaining talk. I really enjoyed that.
Oh, thank you.
I've got my question really is more of a. I'm not sure it's really fair to ask you, but it's more of a dichotomy that you have.
Yep.
Because what you've got is dark matter, which is actually holding galaxies together, and dark energy, which is trying to rip them apart.
Yeah.
Okay. And it seems to me that if you believe that the dark matter is very weakly interacting, and the way I look at that, you must have a lot of this substance, which has a very, very small interactive property, but you've got a lot of a little can give you a lot, which then holds the galaxy together. That's what I understand it. But then you've got dark energy that's actually effectively driving the expansion of the universe.
Yep.
Is there any possibility that the two could be very close related, and that there's some form of affinity between matter and the WIMPs?
Yeah, I mean, first of all, until we prove what we think it is, there's anything's a possibility. But again, solving a science problem is like solving a crime. There's evidence, and the evidence and the symptoms of dark matter and dark energy are very dissimilar. Okay, I mean they're very dissimilar. And if you just forget dark matter for a while, dark energy for a while, there is a relatively simple, could be a simple answer to dark matter. It could be tangibly matter that's out there, matter that's not that dissimilar to our standard model particles, but just different particles. It could be there's just particles. That seems to be the most obvious answer, and it fits most of the evidence. Okay, but to say it's nothing to do with dark matter, we don't know until we prove that. But there's nothing to link it at the moment. And the reason they're very different is, even though dark matter particles is weakly interacting, it's still a damn sight stronger. The pull of gravity that you get from dark matter is much stronger than the anti-polar gravity that you see from dark energy. Dark energy is subtle in the extreme, and it's an apparent anti-gravity that space itself seems to be pregnant with energy of some kind that allows it to expand. It's very poorly understood. There is no simple answer at the moment to dark energy. There may be a simple answer to dark matter, but from a symptoms point of view, symptoms are the wrong word. What am I looking for? They're very different beasts. I mean, and they've been lumped together because they're called dark. The similarities are they're both a mystery and they're both called dark, but they're very different mysteries. I think dark matter is much more possibly round the corner. We'll find it. Dark energy is a different kettle of fish. But until we know, we don't know.
Thank you very much. Yes, I do understand the problem. I studied this 18 years ago.
Yeah, no, really.
It's only just been discovered. But thank you.
Really good question. Thank you.
Yeah. So Simon.
Yes, I'd just like to ask a question about the parameter space, Sean.
Yes.
As it shrinks, as you progress with the technology, is there a potential here to work with cosmological models, astrophysics models, where you're already eliminating some of the wider or off-stream models already and reducing those models? Is that happening?
Oh, very much so. So, I mean, dark matter goes through periods of being the most popular thing in science, you know, and so there's a lot of observational cosmologists that I mean, honestly, they say they found dark matter already. They see the evidence for it, and all these structure formation, the way things form, and it says that these type of particles must exist. So there's a lot of interplay. There's a lot of observational cosmology and theoretical cosmology that goes into that. That are looking for dark matter. And yes, you're right. As we rule out these certain particles, it does constrain the some of the cosmological theory, and there is interplay between the observational cosmologists. I'm not an expert in that, so I can't really say, you know, how it's feeding back. But we're certainly listening to what they're saying, and they're listening to what we're saying. But I don't have any examples. But yes, they're very interested to see if we start ruling out these particles, some of their theories of how things are working will change as well. Yeah, it's a good question. Thank you.
Thank you.
There's a couple of questions in the chat. Are your instruments sensitive to seismic activity from the mining?
Not good question. Not really. I mean, different. We do lots of different science projects, but the dark matter ones tend not to be. They've got enough to worry about with the background radiation. No, I mean, the one blessing is they don't mind a bit of vibration. Not bad at all. And to be honest, you know, there were vehicles underground, as you saw in that video, and they do mining. They do the mining a long way from where we are. Vehicles do go past, but the vibrations are minimal. But no, we're not really sensitive.
Okay. Another one on the chat from David Gwynn. Do those who favour MOND theories instead of dark matter cause you any sleepless nights?
Yes, but not for the reason you might think. They cause us sleepless nights because MOND is modified Newtonian dynamics. Basically, it's saying that, hold on, most of the evidence you have for dark matter seems to be the extra pull of gravity that you're saying. Instead of being missing mass out there, maybe we don't understand gravity as well as we thought. Maybe gravity, if it behaves differently at different acceleration levels or distance levels, it could explain the pull of dark matter. Sorry, that what we think, you know, the evidence that we otherwise put to dark matter. Now, the interesting thing about that is, it's going backward from the problem in a way, but if you can tweak gravity to fit galaxy rotation curves, the speed at which galaxies rotate, but then that model doesn't seem to fit that and doesn't seem to fit that. It's hard to find a coherent model that fits all the evidence, and so there's a problem with it. So it doesn't worry me too much. The other reason it doesn't worry me too much is, look, we're being honest about science. It is like solving a crime. I would say the dodgy looking bloke with the axe, the most most obvious candidate is particles of some kind, but there are other weird and wonderful candidates for the crime, and MOND is one of them. That's one reason it doesn't bother me, because that's the truth. It is out there. The reason it does bother me is somehow that idea fits neatly on the brain. It's like a meme. When it pings into your brain, maybe we've got gravity wrong. It seems to fit neatly. And it's like a story that perpetuates itself. So the one reason that it does make me lose sleep is because it's popular beyond its background, beyond its ammunition, beyond its foundations a little bit. It's more popular as an idea than lent to by merit, a little bit, but it might be true. Who knows?
Okay, well, I'm going to have a question, as it's gone a little bit quiet. Could you say a little bit about eliminating background radiation? And you obviously build your equipment out of material that's brought down from the surface. And my layman's understanding is that everything on the surface is basically, since atmospheric nuclear testing, is contaminated with something. How do you control that or get around that?
There's clever chemists out there who know how to separate different isotopes, and there's clever people that can do that, but they can't do it perfectly. So you're right. All material, not all, but all common materials, including you and I, are made of there's uranium and thorium in us, and they decay. And we're all slightly radioactive. All our food is radioactive. The walls are radioactive. There's radiation in the air. So it's not just from the nuclear bombs. It's there anyway. So forget the nuclear bombs. It's there anyway. there's clever things you can, well, first of all, you can refine them with chemistry, and you can separate out the isotopes to an extent. Some things are better at doing that than others. Xenon, for instance, you can do wonderful separation, distillation with xenon and get rid of almost basically all of the radioactive components of xenon, which is why the liquid xenon technique, the Zeppelin technique, is so good. The other thing you can do is you can grow your own materials underground, which haven't been bombarded by cosmic rays. So there's clever ways of doing it. But you know, it all comes down to material science. The devil is in the detail with all of these things, and engineers and experts in materials are the heroes of this game.
Okay, we have another question in the chat, and from David Gwynn, an excellent talk. Thank you very much. Right, question from Richard. What's your take on the superluminal neutrinos that were allegedly detected in Italy a few years back? Was this simple experimental error?
Well, I'm not on that. I mean, that was all very. Wasn't that an exciting time? So it's very interesting for us, because that of course was detected in an underground lab. That is the Italian underground lab that we are competing against to try and get this next great dark matter detector. In fact, that was in Gran Sasso in Italy. A beam fired to it from CERN to Gran Sasso, and I mean, there seems to be no doubt it was an experimental error. But it was an interesting lesson in science and science communication, that the team honestly thought, God damn it, we think we really understand our experiment. We understand all the timings of the electronics. We've looked at absolutely everything. These neutrinos seem to be going faster than the speed of light. What on earth's going on? Now, they did what they thought to be the honest thing, was told the world, oh, look, we seem to be seeing this, now help us out. And God damn it, 2 weeks later or whatever, sure enough, a loose connection was found that explained that their timings were off, and no, they were not going faster than the speed of light. So it was an interesting lesson in take a big pause before you announce something big, but also even before you admit your uncertainty. So no one thinks that that's true anymore.
Okay, any more questions? Any more questions for Sean? Last chance.
Can I ask a quick question about some of these galaxies that popped up? Well, some people have, over the last decade, it seems to be occasionally there's a galaxy that appears with no dark energy in it, and other times they find a galaxy that's totally full of dark energy. And I'm somewhat interested in they're trying to think of ways of normal baryonic matter being thrown out, for example, or whatever, and it's an evolutionary thing rather in the galaxy itself, but rather interesting. I mean, when you look at these things and if they prove to be accurate, are they any clues to help you with your experiments?
Oh, absolutely. You meant dark matter, you said dark energy.
Oh, apologies. Yeah, absolutely. Sorry.
No. This is, I mean, that's not your fault. It's the people who named it dark energy. It's their fault.
Stupid name, yeah.
Well, although it's a great name. It's just that it was already taken, wasn't it? So I'm not an expert in that, I'll be honest. There's a lot of people who analyze, again, going back to observational cosmology and look at all these galaxies and say, what does it mean? I mean, the vast majority of them, as I understand it, and it's not my expertise, but as I understand it, is the vast majority of galaxies that you see of the various kinds have a large amount of dark matter in them. But there are variations on that. You're absolutely right. There are some that are none, and there's some that are bloody huge and there's nothing there at all, and it's gravitational lensing. So it's a galaxy with just dark matter. So there are variations. What that means, that I leave that to the computational cosmologists and to work out you know about galaxies, now they form and what they can be hit by and what can happen. So that's their topic. Of course, the interesting one that came not so long back was the bullet cluster. You remember that?
Yeah.
So with one mass meeting and one visible mass meeting another mass, and yet the gravitational lenses showed that yes, there was missing matter out there, but it wasn't in the same place. It was finally the symmetry had been split, and the visible matter seemed to have slowed itself down by interacting, but the dark matter can't interact, so it carried on past. So, you know, there we go. So a lot of people spend their times looking at that, and the jury seems to be, for a while, that picture was claimed to be, that's it. Observational cosmology has cracked dark matter. Here it is. But even that's come under, you know, questions from various different sides. So good question. Thank you.
Thank you. Thank you.
Okay. Any more? Any more questions? Your last chance has expired.
Well, last chance, except please do email us, and please do like us on Facebook if you're that way inclined.
Yes, and I'd like to thank Sean for a really interesting talk about a world-leading piece of infrastructure that I didn't know that was there until I saw this talk being built. So thank you very much.
Well, thank you very much. Thank you all. Thanks for giving me some of your time. Thanks very much.
Okay. Second speaker tonight, a short presentation from Andrew Thornett, who is a long-standing member of this group and an enthusiastic amateur astronomer. Andrew, the floor is yours.
Oh, hi. So can everybody hear me?
Yes.
Yes. So how long would you like me to take, given that we're running a bit late?
Shall we say 15, 20 minutes, a few questions, and then we'll wrap up.
Okay, no problems. Let's see if I can get I sent earlier on a copy of my talk to you just in case this doesn't work. So let's see if I can work out how to share my screen. How do I do this? I'm not a Zoom expert. What do I do?
The green button at the bottom.
Green button.
Green button at the bottom. Share screen. That helps, doesn't it? Yeah, this probably gives you an idea of me and radio astronomy, as I can't even work out where the green button is on the screen. And any success I've got is quite amazing, really. Where are we? Somewhere on here. Slideshow from the beginning. Okay, right. Can you see my slideshow?
Yes, that's fine.
It should be a black page saying detecting molecular hydrogen, etc., etc. You got that?
Yes, that's working fine, Andrew.
Perfectly. Okay, which is always a good point to make sure we're starting. Okay, well, thank you very much for inviting me to speak tonight. I'm going to try and not take too long because you've kindly invited me to come back in January and really bore everybody for an hour. I was asked by Andrew to give a talk to motivate people. Now, I don't know what sort of expertise we've got in the group that's watching tonight. I suspect probably an awful lot. One or two of you might never have done any hydrogen observing and might never intend to do so. One or two of you might feel that this is of interest in terms of taking it up, but I suspect a more interesting aspect of this is going to be perhaps reminding you what it's like to be a non-expert coming into a topic like this. I'm a family GP, or a family doctor, I should say, for anybody who's not from the UK. So a general practitioner, we call them here. So obviously I treat people's bodies. I'm interested in astronomy, all aspects of astronomy, radio astronomy as well, but I'm hardly an expert on it. I don't have science background in as much as I've done a medical degree. I'm interested in physics, but I don't have any particular expertise in it. And more important than that, I get very confused very easily by it. But I do a lot of education as a doctor. I've done over the years. I just want to talk to you for a second about something called the Johari window, which you may or may never have heard of. So the easy way to explain this is just imagine that you try to teach somebody how to ride a bike. Now, most of us here probably know how to ride a bike. And you probably think to yourself, that's easy, I can tell somebody how to ride a bike. But actually, it's an incredibly difficult task trying to teach someone to ride a bike. Because what's happened is that most of us have forgotten what it's like to learn to ride a bike. We've got to the stage where things become second nature. And actually trying to deconstruct that and go back to, well, what are the different moves that you make? What are the different things that you've got to do to try and actually get that bike to move? It's actually quite difficult. Even more difficult is if you're trying to teach somebody to play a musical instrument. My son plays the clarinet, and one of the issues with the clarinet is that it all depends on what shape your throat is. So the teacher may put a particular movement of their lips or throat to get a noise out, but their student will require something that's slightly different. And to some extent, the only way the student can find out is by trial and error until one day they actually manage to get it right. And it's those combination of two things, I think, which is there particularly for a non-expert or somebody without any perhaps physics or electronics expertise coming in to try and take up radio astronomy. And I am very much one of those people. So I hope that in a non-offensive way, I'm going to just help you to understand what it is to be like that. I'm showing off the fact that I have a sort of radio call sign there of M6THO. But for those that don't know, that's the foundation exam in the UK, which I did do to try and learn something about radio. But all it taught me about was the legislation around radio. So I didn't learn anything at all about the electronics. And maybe one day I'll go and do the intermediate exam and learn an actual bit about radio electronics. But so far, I'm learning on the fly, as it were. So, right. So take another step. So radio astronomy, as the UKRI has been it's done a wonderful job of actually selling bits and pieces to help people get into it with things like SID monitors and meteor observing, etc. It's great, but let's be honest, it's not what people out there think of when they think of radio astronomy. They think of Jodrell Bank, great big dishes, mapping the Milky Way, finding out the nature of dark energy, etc. And there's a sort of a bit of a sense you sort of perhaps don't get money to SIDS or whatever, sudden unexpected disturbances from flares. It's fine, but it's not really what people want. And so I want to motivate people to know that it actually is quite possible from your backyard to be able to do it. And my backyard is located in quite a large suburban area, about 400 meters away from Tesco's. There is a lot of radio interference in the area, and yet I've still managed to succeed. So first motivating factor is to say it can be done. So what's changed? Well, I initially got interested in radio astronomy probably about 10, 12 years ago. And at that time, a lot of the equipment was really quite expensive. So I think what's really changed for people like myself who are not sort of experts, who have lots of other eclectic interests in astronomy, to get into this field as well, is actually the software-defined radios, which you can now pick up for 30 or 40 quid. And particularly when it comes to the hydrogen line, that wonderful Sawbird plus H-1 filter low noise amplifier that's now available for 30 quid or so, which is quite incredible, isn't it? To be able to get this type of equipment for only a few pounds. And I must take my hat off in particular to the Society of Amateur Radio Astronomers for their Scope in the Box project, which is actually what got me started this in the first place. Which is, if you're unaware of it, is a project they've set up for doing hydrogen line observing. And what's important about it is they've gathered together the various bits and pieces that people need to do it. They've written an absolutely fantastic manual to go with it, got the software ready for it, and then ship it out to people for about $350. They only ship within the US. But when I asked for help, I was very kindly sent a complete list of all the parts that was necessary, including some pictures, so I could go and order it from amazon.co.uk. And I was able to get hold of everything and get started. So before I carry on, I've got to give some thanks. Now, if your name is not actually mentioned here, I would like to give you my apologies. There have been so many people who've given me help on this that I couldn't really list everybody, but I just picked up some particular names of folks who really I would just not be here without. So I don't know, is Lester on the call at all? Is he not here today? No. Well, Lester is in charge of the scope, or I don't know if he's created it or just in charge of the scope in the box concept in the States. And it's through him that I got started in this. So I have a very great support for him. And then Ted, I know you're here. Oh, I mean, Ted, I wouldn't be doing this without Ted. It's simple to say that. He has been my mentor and absolutely fantastic. I mean, to me, his best phrase is, keep sending the questions. How on earth he can keep saying that after the 400 million of them that I've sent to him, I really don't know. absolutely silly questions I ask and not understand it. And he just keeps sending me more and more stuff. He's absolutely fantastic. And his incredible easy radio astronomy software suite, which I'm going to be mentioning more of now and an awful lot more about in January, which just, wow, I mean, that just takes people who aren't experts, it just allows them to do miraculous things. And then I've got Andy and Paul here, who particularly been helping me out a little bit with hydrogen, but also on some of the other stuff I'm doing with the VLFs and the magnetometer and meteor scatter stuff. And again, they give me so much of their time, and I'm very grateful to them. And to anybody else I've not mentioned, I apologize for not having mentioned your name here. And you're going to be finding out about the Ptarmigan Trifid Array, which is what I'm using for my observations at the moment. So for Andrew Thomas there, the other Andrew Thomas, that is, for 2 Andrew Thomases around, for that wonderful gift. Thank you, Andrew, very much indeed for that, which has been fantastic. And for a particular reason, which you'll find out in a minute or two, which is really important, which people don't think about when they're doing radio astronomy. So I'm a great believer in full disclosure and honesty. So yes, I've been told that I've got to encourage people. So there's a few howevers on this. I've actually been off work ill for the last 2 or 3 months. And I will admit, I've put hundreds of hours into this project, and it has required a phenomenal amount of support to get there. This isn't just something you can just pick up and get working, especially if you haven't got that expertise or knowledge. And just be honest about that. But it is very exciting, and of course, given this summer and just how awfully cloudy and raining it's been, it's rather exciting to do something like this, which works even when it's cloudy and even when it's raining. So yeah, I'm very excited, and I'm going to be doing more and more of this radio astronomy stuff. Right, so here's the scope in the box, just to give you an idea what it is. So it's based on one of these Newelec 1.7 gigahertz GOES satellite mesh satellite things, about 30 odd pounds off Amazon. I've got to admit, I never actually really got that one to work because then I've given the Trifid array, so I didn't really spend much time on it. It's not quite tuned perfectly. It's 1.7 rather than 1.4, but people do get them working. But it's worth saying that Newelec have actually just produced a brand new one, which is actually tuned at 1.4 gigahertz. So that should work somewhat better than the 1.7 one, although they are charging a bit more money for it. It's worth saying. Okay, so I'll come back to that a bit later. Okay, so here's the, if you've never seen a Ptarmigan Trifid array, here he is on the left-hand side. That green thing comes in a nice dark military green, or you can have dark military green, or dark military green when it comes in the one color. They're a bit rare. As you can see, it's 86 by 86 centimeters in size, and a 16 dipoles on it by 4 by 4, but each about 97 millimeters in size. The reason I got that information is somebody asked me for it. I'm not entirely sure exactly what it means, but there we are. And there she is, or he is outside on the first night from me trying to get a drift sample going across the Milky Way, came across the zenith. This array has one particular feature which makes it stand out from every 3-meter dish that's out there, even a 1-meter dish. And that is that my wife has given me permission to have it out on the patio. That's the thing that people don't think about, especially if you haven't got a great big field to put this stuff in, and you've just built an extension on the back of your house, and your partner is very concerned about the look of everything. It's really important that whatever piece of whatever you're going to put out there is something that's going to be acceptable to the powers that be. And this particular one doesn't look particularly like a radio telescope, and that apparently is what makes it stand out, and has given me permission to keep it outside sort of semi-permanently, which is quite incredible. Plus, it's actually effectively getting the hydrogen line, which is brilliant. So here we are. I started off using SDR Sharp as my software to put. This is what came with the scope in the box. So for hydrogen line observing, for those that do it, you'll know that there's something called IF average, which is a plugin for SDR Sharp, which allows you to average together data over a few minutes. I don't know. It's an interesting plugin. It doesn't. In my experience, I couldn't seem to get it to work with the latest version of SDR Sharp. I don't know why. It seems to be a problem with getting the bias T to work as well, the latest version. but there's an older version of SDR Sharp which comes with the scope in the box in a box package, which works perfectly. And Sarah have uploaded already into that package all the plugins for you, including a whole gamut full of other ones, which are all there ready to go. So it's worth definitely getting that particular version of SDR Sharp from Sarah. I'd recommend it with that one. So here we are. So this is the data as you sort of get out of it when you put it straight through. And then this shows what happens when you've actually done a bit of calibration. So you can see there, I've circled it to show the two hydrogen peaks. Now, the first issue I would say, I talked about the business of trying to ride a bike and perhaps forgetting what it's like. To you guys, you look at that, they go, yeah, it's obvious that that's going to be the signal. But, you know, for me, that was not obvious at all. I didn't know what the signal was, those little spikes that were either side of those peaks. I had absolutely no idea what I was looking for. And it's a good example. When you're going to ride a bike, you don't know what it takes to actually keep yourself upright. And then when you've learned to keep yourself upright and balance yourself, you can't actually remember what it is you ever did to actually learn to balance. You never forget it again. So I will never forget now that a peak looks a bit like that rather than one of those spikes, which is interference from a neighboring channel. But bear in mind, if you're trying to tell somebody about this, that, you know, that's the sort of information which they won't necessarily have to hand and need to be taught. Here you can see that it's gone two different parts of the Milky Way. You can see the slight difference between the peaks, which as yet I haven't actually learned to understand what the differences are, but I'm sure indicates something. So just saying that the expected frequency. So again, what is the expected frequency? You guys, it's obvious. Hydrogen's 1420.405, but when you're coming in from nowhere, it isn't obvious what it's doing, especially when you can't see it. You don't know whether it's because you tuned in the wrong place or something else that you've done wrong. I mean, I did when I was doing it. Now I had 1.2, which one of the patch cables I was using was broken. Sometimes when you buy them off Amazon or wherever, they aren't very good and don't work. But if you don't know what you're doing, you don't know if that's broken or not. Right. So again, for us coming from outside of radio astronomy, it's worth, when you're speaking to people, doing some comparison with things that people will understand. So in astrophotography, we have things called flat frames and dark frames, and calibration of the radio telescope is a bit like that. It's a similar sort of job that it does to average out the background and the effects of the instrument, and it allows you to get more detail out of the signal than you would otherwise be able to see very easily. And so the 50 ohm load here, which was a simple way of achieving it. So plug one in, just a picture of anyone who's never seen one before. And this shows the difference between a calibrated and a non-calibrated image. So on the right-hand side, again, for most of you guys, this is all going to be something that you've seen many times before, but you've got the original sort of SDR one here and SDR Sharp. And on the left-hand side, you've got the effective IF average, which is, has taken that background out. The interesting, so you can see that the one on the right, you can see the sort of peaks up at the side, and that's gone more flat on the left-hand side. What I find interesting here is that for me, I seem to get a better effect rather than using a 50 ohm dummy load like that to actually just point the telescope at a different part of the sky. When the Milky Way was out of the way, it seemed to get a much flatter trace. Although I have had people comment back to me since that there's always some sort of hydrogen signal from the sky, so that might be losing some of the signal to noise ratio. But just mention it for what it's worth. I picked this up off Stargazer's found Steve BZ. I don't know who Steve BZ is, but it's a brilliant graph he put on there, to give him credit for it, just showing the effect of electronics on noise on the plot, at least in his experience, with the one on the left quite noisy there with spikes, and on the right when he actually switched off some adjacent electronics. Right, now I sort of mentioned easy radio astronomy software that Ted's written. This is a brilliant collection of Python scripts. You do have to learn how to actually launch a Python script, which may seem really easy when you've done it before, but it took me a couple of hours to work out how to actually do it. But then eventually I got it working, and now it works absolutely fine. And as an alternative to using the SDR sharp IF average, there's a collection routine in there which works very well. And it's got a rather neat factor that you can actually calibrate by taking a sample, every other sample that's 3 megahertz away from the 140 to 0.405. So therefore your calibration sample will actually follow things like temperature changes in your radio equipment over the night. So it's really quite clever. And it produces these phenomenal graphs, which you don't need to understand. You just press a button and 250 odd of them churn out at the end. So here you can see that this is towards the beginning of my data collection, a 4-day drift scan just over the zenith. And quite nicely, I'm getting a couple of peaks there that are matching the Milky Way on both sides, which made me feel very, very excited, very happy, and kept me going. Because that's another thing when you're just starting off in radio astronomy. It can be incredibly frustrating if you can't get things to work. I mean, bluntly, if you're not getting any results, and this goes on for months and months, you get to a stage where you give up and you want to move on to something else. But if you can get some results that come out quite quickly, then that's going to stimulate and encourage you to keep going and to actually sort things out and to get better results and to take it further and then deal with the difficulties. So a graph like this really is extremely exciting. Obviously, it's been the green is my data, and the rest of it is a straight plot that EZRA just plots it over the top of, and then it gives you other graphs such as these, just showing particular traces at particular points. It shows you the Doppler shift. You can see here that was over a few days, and then starts to map it out for you, including I don't know if I've got one here. I don't think I do, but if you've got a few different elevations, it starts to actually map out for you the radial arms of the Milky Way, which I may have in a minute or two to be able to show you that. It's just a little bit of testing for myself here. So I found online a simulator of the Milky Way and tried to put in the same coordinates, and lo and behold, I've managed to produce a graph on the left, which is mine, which looks at the same sort of peaks, not as powerful as the ones on the right, but similar as the one on the right-hand side, which is the simulation. So again, I felt very happy about that I could believe I was getting some sort of data that made some sense. And I tried, I can't take credit for this. Ted here very kindly looked at my data and did some calculations for me on it, and came to the conclusion that my beam width was about 15 degrees or so on the array, which interestingly approximates to about the same as an 86 centimeter dish as well. So there you are, 86 centimeter array, 86 centimeter dish. Makes a lot of sense. Right, so this is where I get my saw and my my drill out. I created this little sort of table device to allow me to try and change the elevation to do it, so to look at different parts of the sky. My wife was unhappy because I nicked half her paint for the fence to paint it up, but got it working at the end of the day. All that stuff underneath it is the computer that I'm using for actually and the receiver for actually picking up the data. So somebody kindly gave me an old laptop, well, at least not a very powerful laptop, more accurately. And here you've got, and there's my receiver on the left-hand side. This also highlights the really big problem that I had with this. Being the UK, the major issue that we have is humidity levels of 100% a lot of the time. And it was demonstrated by the fact that that receiver is mounted on a chopping board made of PVC, but I'd previously had a chopping board made of wood. And after a couple of weeks in that, it was actually growing fungus all over it, which gave a good example of the issue. So the dehumidifier is one of these little caravan dehumidifiers you can buy for 50 or 60 quid off Amazon. So I've shoved it in my box, and it's got a tube that goes through a hole. There you can see the plastic tube, the outside world. And it's done a brilliant job of keeping the thing completely dry without radically affecting the tracers at all. I know you think, well, actually, that's really bad news. That's going to cause interference, but it doesn't make a big issue. I have slapped a load of silver foil over the top of the box to try and limit stuff going up to the antenna array, but it's still producing quite a nice trace. And here we are. So 3 different elevations there, showing us starting to pick up data, as you'd expect, different parts of the Milky Way. And here I said about starting to map out the Milky Way arms. And you can see there it's starting to put the different elevations together. And here I've managed to find a little plot of the Milky Way and overlay it on there. And very nicely, it shows that the peaks in my data are starting to follow the Perseus arm. So I'm extremely pleased with that. Here we are. This I don't quite understand. Perhaps Ted a bit later on can explain to me what it means. But it says about the closed masses, solar masses. I assume that's at different areas in the Milky Way. Let's start on the process of I don't know where basically one of the problems with easy array is it produces a whole load of plots you don't understand. But I think something to come back to and learn. Right, now I did say about the new Newelec 1420 megahertz or 1.4 gigahertz dish. I have actually got a hold of one of those to try, and I haven't got very far with testing it yet. I did a little bit of initial testing, and enough to show that I was able to pick up the hydrogen peak. You can see the one on the right-hand side is my Pharmagun Trifid, and the one on the left is the 1420. It's at a time of the day where there isn't much of a peak, but at least it shows something. Right. So just to finish off, a little bit of advice I would like to give to people starting on this who don't know very much about radio astronomy or radios in general or electronics. First thing is it's really, really important to get lots of supports and advice. And the BAA and SARA are fantastic organizations with people who really care and who put lots of effort into helping you. And I can't thank them too much, and I can't recommend them too much. When you're doing it, you do need to put lots of time. This is not something that you're going to go, I mean, for an expert in the area, fine. But if you're like me, you're starting from nowhere, then you're going to have to spend a lot of time to get it working, and realize that there are going to be times that you're not going to get things to work. Probably quite a lot of times is to work, and you have to keep going. And really, that's part of what it's about. It's making mistakes, starting again, keeping going. Don't feel embarrassed that you don't know enough. I mean, that is actually, when you're dealing with people who are such experts, it is so easy to feel embarrassed and not to ask questions. But I think realize there's a lot of expertise, make use of it, and don't feel embarrassed. One thing I have noticed is not really meant to be a criticism of anybody, but some people are a bit inclined to perhaps be perfectionists and come in and give you advice and say, oh, you should keep changing that, you should do that, you should do the other, you should get it better. But actually, to some extent, if you can get it to work and you start producing some results, that's what's going to give you the excitement to keep going, and then you can come back to it later on and perfect it. So it doesn't always have to be perfect right at the beginning. And finally, one issue that I found, which is quite an issue, is be careful estimating elevation and azimuth. I thought, oh, it's obvious 45 degrees, that's 45 degrees. It turned out to be a few degrees different to that. It actually made quite a difference on the graphs. You can actually get some great apps on your phone that will do both compass and inclinometers, quite free apps. So there's actually no excuse for not actually getting out there and measuring your elevation azimuths and then putting them correctly into the software. And that's me done. Thank you very much, everyone.
Andrew, thank you very much. For those of us who haven't even started yet, that's quite encouraging. And as for perfectionism, there's always time to buy a 10-meter dish.
There's no way I'm going to be able to put a 10-meter dish in my garden.
There's always time to buy a bigger garden.
Yeah, I have to have a new wife.
Anybody want to add anything? Just first, Andrew, there are some pointers being put into the chat feed,
Oh, chatter.
which
I haven't seen
you may find of interest, with links to various. Ted's put a link in. Martin Kinder's put a link in to useful things that if you may not have found yet. Does anybody wish to add anything to Andrew's presentation or deliver good advice in a spirit of friendly cooperation?
Oh yeah, any advice is readily accepted. I've got nothing nothing to that I need to be particularly keep to myself or anything.
Quick question: where'd you get the antenna from? I can't find it on their website at all. The new
Neuralec.
Yeah.
Amazon.com, but I think I saw it on Amazon.co.uk the other day.
Well, I've gone through their section and it doesn't mention it at all.
Yeah.
Which is strange. I've just been looking. Yeah.
I mean, it is a bit different to the 1.7 one in as much as it's the antenna's ever so slightly bigger. The feed is bigger.
Yeah.
The stalk is bigger. I'm just having a look.
I just wonder if you've got a link to it, because I'm darned if I can find it. I've got the filter. It's already sitting in my Amazon box. So I've got the preamp filter, SAW filter. Yeah.
Yeah. The I mean the Sawbird, you mean?
Yeah.
Oh yeah,
I've got that already. I've got that. It's already in my Amazon box.
So, yeah. What SDR are you going to use?
At the moment, I've got the one called 100 quid thing. Oh dear, I forgot what it's called now. I've got it. I've been using it, but I just keep forgetting what it's called. RP. I think it's R. No, I can't. PBR, something like that. One. It's an entry level £100.
Well, the one I'm using is the RTL SDR V3, which is cheaper than that.
Yeah, no, this one I use for radio amateur stuff. I've been using it for some while.
Yeah,
so I think it's a bit better. I think it's quite good performance for the, but it's still an entry level device.
Well, I'm sure it'll be absolutely fine.
Yeah,
I just put a link on there for the 1.4 gigahertz on the American Amazon.com.
Right, I've just clicked. Oh, thank you. Yes, perfect.
Yes, I think Ted's put a link in as well.
Good. Oh, thank you, Ted. Yeah,
looks vaguely similar.
Brilliant.
Okay,
oh, it's at 9% discount. Thank you.
Okay, Martin Kinder, please.
Yes, first of all, well done, Andrew.
Thank you.
That really is an achievement. That really is. A lot of people aspire to doing this. At least you got your finger out and did it. And that I've been watching your progress on the SARA forum for a couple of months now, and I've actually been collecting bits. So just to let you know, I'm following you along. I actually this is actually my summer project for 2023, and of course we're now in November. I haven't really started apart from putting together a 1.6 meter dish that I bought from Alamelia 20 years ago for exactly this. So you've taken 2 months. I've taken 20 years. And you beat me. So I would say that's pretty remarkable. So well done. And I put a link on there because I saw you post about digital filters. With a URL for the designing one for 1420, and I followed through. It's actually fairly straightforward. I've built it into digital filters before, when I used to be a proper radio ham before I went deaf. And if you get stuck, you just get in touch with me. I'll help you out. It's easier to perhaps show things over a Zoom link and talk you through that way, rather than through a forum of some sort. So let me know if you need any help.
Oh, wonderful. Can I just ask for your email address, Martin?
You're on mute, Martin.
Or perhaps if you're happy to, you could put it in the chat if you don't mind sharing it. Oh, thank you. I will take you up on that. Thank you.
Okay. Tony.
Yeah, hi there. I did post on the BAA RAG IO group the other day about this crowd supply thing I'd found. I have no relationship to it, but it's at. I put that link in the chat that they're producing a dish especially for radio astronomy now as well, with a guaranteed feed and things like that. And I think it's about $180 or something like that. So it's a good way to get, if you as I said in the chat, if you don't dive in scrap bins like me, and you've got nothing, it's a good way to start.
All right, yeah, I've just seen that. It's very good, isn't it?
Yeah,
it's very good. Free worldwide shipping.
Yeah. I would imagine that's probably quite similar to your ptarmigan type aerial.
Well, it's an interesting question. I have had somebody comment that they feel the ptarmigan trifid probably, in their view, loses quite a lot because of its design. But whether it does or doesn't, as I mentioned before in my talk, it passes the wife test. And if you're going to have something sit outside on the patio for the whole year, it's got to pass the wife test. So whether it's the best design or not is really irrelevant.
Well, with all those dipoles and combiners, there must be quite a lot of loss as well as gain. Obviously, the gain is with the wife, though, so that's the main thing.
Well, that's. I mean, various people said it looks like a barbecue or various other things. So that seems to be the really important thing here. So I mean, I think that was what the other individual actually comment. Wasn't yourself, in case anybody's wondering, it wasn't yourself. But I think, yeah, whatever. It's picking up hydrogen. That's what matters.
Fantastic.
If there are any ex-signalers in the audience who wish to contact Andrew with a bit of technical information, I'm sure he would be delighted, because I'm sure there's people here of the same vintage of ptarmigan trifid.
It's amazingly difficult to find information about it.
Yeah, it was secret.
It seems to be a very rare aerial.
Yes, it was secret. Anybody else want to join in?
So there's a comment there about interdigital filters. Now that I'm doing this, I'm really going bonkers now. I'm really trying to not only run before I can walk, I'm trying to swim the channel at the same time. So I've now decided that I'm going to build an interferometer. I mean, why not just try and do the impossible?
Okay. Thank you, Andrew. That seems to have generated an awful lot of interesting discussion, which I think is the real point of this forum. Anybody else want to join in? Say a few words. Otherwise, I will just say, please join us on the 1st of December for the Christmas lecture and close the meeting. Thank you very much, everybody, and good night.
Thank you very much, Andrew.
Bye. Thanks all.